Today, we shall go to the next lesson of rotation. Last day, we have seen the issues related to torque, measurement of torque, etc., etc. Today, what is angular momentum? Angular momentum. While we are on the subject of angular momentum, please recollect your lessons of linear momentum. Linear momentum. Linear momentum P was measured as mv. I think you remember that, where mass is the mass of the body, v is the linear velocity of the body, and p was called the momentum. And since velocity is a vector, so its product with mass, so momentum p was also the vector. Now recollect, what was the physical relevance of the momentum? The physical relevance of the momentum was actually, if there is a body which was moving, and somehow it comes contact with another moving body or another static body, whatever it is, if they come together, which in physics we call them collision, then what is the resultant momentum of the two bodies? One is going this way, another is going this way. Of course, they could, if they do not strike exactly center to center, they may go in different direction also. You collect what was momentum and what is the physical relevance. The physical relevance was, if a moving body comes in contact with another moving or static body, then what is the result? Keeping that in mind, we come to the point of angular momentum. To discuss angular momentum, what do? We take any body, any rigid body. We take any rigid body as a laminar body. That means it's a very thin thickness, and we consider that there is a small hole here, say this is the axis of rotation. A, and say this is O, and this is V. And let us say this whole body is rotating in this direction with some angular speed, omega. Now, you consider any other point on the body. Let us say this point on the body. This point of the body, let us say this is the point P. And then this point P is actually rotating in a circle. Is actually rotating in a circle like this. If it is rotating in a circle like this, then this point P has a tangential linear velocity v. And if we join this point P from this axis of rotation, let us say this is distance r. And let's say this is called the position vector. This is called a position vector because this has the xy coordinate, so this is r. And this is v, which is also a vector. We know there is a direction of this tangential velocity v, right? In that case, angular momentum of point P point mass, because this word point as a mass, angular point mass P is defined as what? Defined as the vector cross product of the position vector, product of the position vector, and momentum of this point, right? Where P is a momentum. There are too many P's. Uh, so there are too many P's. So let us do one thing. We do not call it P anymore. We call this point, say, X. Here also, instead of point P, we call it point X, point mass X, where P, where P vector is linear momentum of the point, linear momentum of the point X. And what is the linear momentum? We know P is the linear momentum of the point X. It is the mass into velocity of this point, which we have seen in our earlier chapters. Linear momentum is equal to mass into velocity. And this angular momentum is often referred to as capital L, often referred to as capital L. So, capital L is equal to, L is equal to R into M into V. And there is no sine theta. Let me write it here. Since theta is equal to 90 degrees. Listen to me, why theta is equal to 90 degrees? Because this is a position vector, which is actually a radius of this circle. And this is a tangential velocity V and tangential potential P. So this angle is always 90 degrees. Whatever the body or whatever the discussion you do, this angle is always 90 degrees. So linear momentum of the point X is L or V, which is also equal to V equal to R omega, V equal to R omega, V equal to R omega, which, so this is also equal to M R square omega is the angular velocity. So I repeat once again, by definition, angular momentum is the cross product of position vector and linear momentum of a point mass. And R cross P, as per vector algebra, it is RP sine theta. Now theta is always 90 degrees because this is the tangential velocity we are discussing about. R is the position vector, is always the radius of the circle. So theta is 90 degrees. Therefore, angular momentum L is equal to RMV. And since V is equal to omega R, so this is equal to R mr square omega. So let me write here, since V is equal to. Now, if you consider all these points of X, another point Y, another point Z, another point, whatever point, all these points, then what will be the total momentum of the all such points? So, total momentum All such rotating points is equal to, which is designated by L, capital L, is equal to sigma A r square omega, right? Sigma m r square omega. For the sake of mathematical representation, sometimes we write r, we write I here, and here we write summation over I, etc., etc. M, we write I here. These are all mathematical representations, but omega is definitely angular velocity, same for all the points. Now, this is equal to, very surprisingly, what if we come to a very surprising point, sigma mr square is the torque that we have seen last time. So this is the moment of inertia. So moment of inertia I omega. So what we finally arrive at, L, or angular momentum, is equal to moment of inertia I into angular velocity omega. Now compare these two. Linear momentum P was equal to product of mass and linear velocity. And in rotational motion, it is a product of moment of inertia and angular velocity. So this analogy of these two chapters still remains. Linear velocity has been replaced by angular velocity, and mass has been replaced by moment of inertia. That we have seen earlier also. In rotational motion, the quantity of mass behaves as if it is the moment of inertia. Now, there are some special properties of this angular momentum. Like you have seen in linear motion, there is a principle of conservation of momentum, right? Here, here also, the angular momentum, angular, this is called the principle of conservation of angular momentum, and earlier it was principle of conservation of linear momentum. It works in the same way. For example, you can take some example. Let us say there is a, let us say there is a, let's say there is a body, regular or irregular, whatever you say, there is a body, and so this body is rotating over an axle. The body is rotating over an axle. Say this is rotating over an axle like this, in this direction. And you have another body of same shape and size, same shape and size, same shape and size. So so moment of inertia of this first body is also I. The moment of inertia of the second body is also I. Now, if you take an experiment, the first body is only on the axle and it is rotating with a angular velocity omega. Then its linear angular momentum L is equal to I omega. Now, if somehow you can bring this second body onto the axle, like this, which is of course practically very difficult. You can bring it onto the axle. So then it becomes two bodies, and it will have two moment of inertias, which will have total moment of inertia 2I total moment of inertia 2I. So automatically its angular velocity will become omega by 2, so that the momentum, angular momentum, amount of angular momentum still remains I omega. I repeat once again. Suppose there are two exactly similar bodies. One body is outside the axle and one body is rotating on an axle with an angular velocity omega. So if it is rotating on angular velocity omega with inertia, moment of inertia I, its angular momentum is I omega. Now, if you can carefully bring the second body onto this axle once again, then there will be two bodies on the axle. Two bodies will have two identical bodies, so their total moment of inertia will be 2I, and automatically its angular velocity will be half. That means the total body, the two wheels together will start revolving with half the speed, so that its angular momentum value still remains I omega. You can take another example. You can take another example. Let us say, let us say this is a body. Let us say this is a body which is rotating on an axle. Say this body's moment of inertia is I1 and it is rotating with an angular velocity omega. So that it is angular momentum is equal to I1 omega. Now let us say this body is made of some kind of a plastic or some kind of non-rigid material. And let us say during revolution, what happens when it is revolving very fast? Let us say its body gets deformed. Say this body gets deformed. If the body gets deformed, its moment of inertia will change. It will become, say, I2. And automatically its angular velocity will become omega 2. And let's say this is omega 1, this is omega 2. So this will become I2 omega 2. So its angular momentum will become I2 omega 2. And this I1 omega 1 and I2 omega 2 will remain same. That means if the two bodies, or if they, this is the way, whenever they are in contact with each other, in rotational contact, I mean they should be on the same axis. In rotational contact, then automatically the angular momentum of it has to remain same. Has to remain same. Then there are some practical examples which are given in your textbook. You can check them from your textbook. It's a practical example. Say there is a man here. Once again, let me say I'm not a very good artist. The man is, say, standing on a rotating disc. This is a man, and the disc is rotating. Disc is rotating like this. The man is standing on a rotating table, and say this man has two hands like this, and in these two hands he carrying two, say, heavy weight. And this man is, the table is rotating with angular velocity omega 1 say. Now, if this man now, you can yourself do it if you have a rotating table. Then he is on the same rotating table. But now what he does, he extends his hands, and these are the two heavy weights. What I mean to say, these two weights are pretty heavy in comparison to the man's own weight. If you can do this, see here the radius r of this weight is only this much. Here radius r is larger. Radius r is larger. And since moment of inertia is mr squared, so here moment of inertia I2, here moment of inertia is I1, definitely I2 will be much more than I1. If you spread your two hands to a long distance, the radius of these weights increase, so moment of inertia increases. But if you are on the same rotating table, so if moment of inertia increases, obviously this angular velocity omega 2 will be less than omega 1. That means when you spread your hands wide apart, your speed becomes slower. And if you bring your hands very near to your own body so that the moment of inertia lowers down, your speed will automatically go up. How? Why? Basically, in both cases, the angular momentum L has to remain same. In order to keep the angular momentum same, this will happen. Okay? Now, we shall take a small recess here and then we shall next go to the next topic on this.